takes time, it seems so. Okay, so let me proceed. Yeah, so it has started. Okay, I was just mentioning that that the topic under our discussion, that is the concept learning. And so let us start with one of the examples to understand what is the kind of learning task that we are referring at here. Uh, Suppose you would like to find out a day uh, which is, which is good for enjoying sport. Now, there are different attributes of the day that that is your input to this particular task. So, based on those attribute values, you have to predict whether the day is good for enjoying sports or not. Say this is these are certain attributes which I have shown you here in that in the list is there. I mean, with that blue marker, you show the name of the attributes, and all the red followed by the corresponding red marker. You find out the you can see the values of the attributes. So the attribute set is sky condition, humidity, temperature, wind, water, forecast, and the set of possible values for each attributes, those are also listed. Okay, so here the problem definition is in this way, that for each attribute you will have a value. So that would give you that combination will be given to you, and then you will be asked to predict that whether uh, that day is good for enjoying sports. That's what I mentioned. Now, naturally, for the learning, you require experiences, and there would be label data set for that. Okay, so this is the problem. So this is what is your learning task. Now, you have to make a hypothesis, so that hypothesis means that is a representation of your of your in this case, if I consider, it's a kind of uh, it's a kind of formation of a formula, or you are uh, going to learn a formula where each attribute set will be expressed like a Boolean literals. Each attribute values will be expressed like a Boolean literals, and then if those values is a combination of the literal value, that will tell you that whether your prediction is either true. True means here it is true for enjoying sports, or false. False for enjoy. I mean, which means you cannot enjoy sports. That is the kind of prediction. So we will. That is your learning task. It should be in the form of a Boolean function on the attributes of the day, and we'll see also how to express the the corresponding Boolean variable given the attribute value. So how the Boolean literals are formed, variables are formed, that also you will see. So find the right hypothesis or function from historical data. So that is the learning task. You have to express them in the form of a function. So you have training examples. So some training examples are listed here. And this example is taken from Mitchell's book itself. So you see that there are only four no, such combinations which are provided to you as an example. So we have four such records, four training examples, and you can see that in each column uh, each column is represented by an attribute, and the last column, it is actually giving you the functional value of that Boolean function, what I mentioned, either in the form of yes or no. That means whether you are enjoying sports on that day or not. So the first one, you can see those values like sky is sunny, temperature is warm, humidity is normal, wind is strong, water is warm, forest forecast is the same. Then it is 1. So forecast same, I hope you have understood that you are predicting something with respect to, say, for example, today's attribute set. So you are considering the observations on a particular day, and these are the observations of that day, and you are predicting for something, for example, for the next day, maybe something like that. So these are all context dependent. So the next three combinations where the value is yes, that has been shown, and I have intentionally put them in the form of a function as we are more familiar to familiar to that notations. So you have the corresponding values of the attributes in every position, and then the value of the function. And there is only one record where you get the value 0. So you have both here negative and positive learning examples, and your objective is to learn the target concept C. So this concept learning, the term concept is associated with this function here, right? This Boolean function here. That is the concept you are trying to learn here. So this is which is a Boolean function, as I mentioned. Right. So this is a task that we have to derive a Boolean function from training examples, such that it basically satisfies at least the training data set, and then you can extend that applications, extend that definitions to the unseen data also. So when it comes, you just put those values in the function and you evaluate and get the value. I think somebody's microphone is unmuted. Please mute it. So you have to find an hypothesis H, which is trying to represent the target concept C. See, target concept is not known to you. That is the problem you need to solve. So the nature of target concept means that it's a Boolean function, and partially the functional values are given to you, and you really do not know what are the functional values on the unseen combinations of attribute sets. So whatever you derive, it would be some kind of I should say assumptions, or it would be some kind of approximations of C. You may not say exactly that has become C. So, but there could be various such hypothetical Boolean functions. Okay, various such hypothetical Boolean functions. If I consider this particular example, that means how many variables are there? How many attributes are there? There are, if we go back, 6. How many are there? There are 6. No? 1, 2, 3, 4, 5, 6. Okay, and so if I consider that each variable, of course, it is not that they are all binary valued attribute sets. They could be multiple values, but just for the sake of simplicity, let us consider, say, all are binary valued attribute sets. Like sky is sunny or not sunny, temperature is warm or not warm, something like that. Let us assume, but we'll go through that examples later on also. So the question is that if I give you these 4 functional values, with this kind of informations, so how many functions are possible? How many functions are possible so that that would satisfy all these functions, all these 4 records? Can you tell me how many functions are possible? Pardon?
2 to the power 6.
2 to the power 6.
Somehow I could not hear properly. Can you tell me once again?
2 to the power 6.
2 to the power 6. I meant 2 is to the power 64.
2 to the power 6. I mean, how many combinations are there? You are saying number of combinations should be 2 to the power 6. That is okay, right? If they are all binary valued, number of combinations is 2 to the power 6. But the question is that how many functions are possible out of them?
2 is to power 64.
Power 64.
Right. That is total number of functions. That is a total. If I say that each function is a hypothesis, each each that is hypothesis. Each function is hypothesis. So your hypothesis space consists of 2 to the power 64 elements. Okay. Now the question is that out of them, how many functions or hypotheses we are talking in the almost in the same way, same term, they are equivalent here. How many of them will satisfy these training examples? So that is the question. So how many of them will satisfy the training examples? Pardon?
Yeah, got it, sir.
Have you answered?
2 power
Did you-
62.
Please tell me once again.
2 power 62,
2 to the power 62.
because there are 4 values
Okay.
2 to
and
the power
a total of
60.
64 combinations. So we are
Yes.
excluding those 60. So 2 power 60.
2 to the power 60.
Yeah.
Is it? That's right. So not 2 to the power 62. I think that is fine. Huh? So everybody agrees? So which means that you have so many possible hypotheses, and out of them, one is actually this target concept. So you try to understand the challenge in this problem. So what is the solution?
Sir, I have one question here.
Yeah.
Sir, what's the difference between then target function and target concept? Sometimes we are telling concept and sometimes functions. So what the
They're
difference?
same. You don't confuse yourself. They're same. Yeah. Okay. If there is something written function and something written concept, they are all synonymous here. Okay. So so that's what I was trying to tell you. So what is the solution in that case? So if you have if you have so many possibilities, then how do you learn? Can anyone tell me?
Sir, we need some learning algorithms so that we can give a training data and program, and it will give a model so that we can use for testing purpose.
No, you are saying approach, some kind of approach, and in a very generic. I'm just trying to understand this particular problem. That you have so many functions, possible functions. There were 60 possible functions. So what is coming into your way? What is needed here to learn the
training data?
You need more data. Exactly. You need more data. As you can see, of course, if you need data for all 64, if you get 64 data for all 64 combinations, then you have a kind of empirical function itself, right? But that is not our objective, and and that is not also possible. That is not also pragmatic. That whole input space will be observed, and then you should learn. So that is a kind of trivial learning in that sense. So, but what is required here, that you need to go through. I mean, you need to get at least certain amount of data, so that your learning becomes effective, and I should say effective in that sense, and also it will be robust. Whatever you learn, it is trying to be. It will try to get you the more or less similar representation of the target concepts, right? So that is the importance of data in this kind of learning. So how are you representing this hypothesis? Again, this I told you, hypothesis, function, concept. You tell in term. I mean, all you consider synonymous. Hypothesis is something which needs to be established, right? As you know, that there is certain kind of impreciseness is there, and it needs to be established also through more observations, etc. And here hypothesis is in the form of a Boolean function, because that is the form of the hypothesis. So what is the form of these functions, Boolean function? That we would also be restricting ourselves. Now you can have different kinds of Boolean functions with Boolean variables. You know that using those binary operators and or not, you can have so many different expressions. But in this case, we'll have only one kind of expressions, and that is what is written here. I mean, it is a conjunction of constraints. What does it mean? It means that all your Boolean variables which are expressed from that attributes by attributes with certain value. So the literals are formed from the attributes and a value from the attribute domain with that equality operations. So attribute value attribute equals some value. That is what is your Boolean literal here, variable here. So either it is true or false. If it is true, if it assumes that value, it is true. If it does not assume that value, it is false. So that is the only form of attribute value. So what are the examples of this literal? Say you have seen that I keep referring the sky. So you give me one Boolean literal. So what should be the attribute Boolean literal value here? It should be. Can anyone tell me?
For a sky, it should be sunny or rainy.
Yeah, no. You just express in mathematically. So I told you that you express in the form of a functional, in the form of a variable, Boolean variable. So it is sky equals sunny.
Sir,
Right?
in 0 or 1.
That is the value, but no, that is ultimately the variable's value you are pointing out. So true or false?
Is sky or a sky bar?
No, it is not sky or sky bar, because sky is the attribute set. So whether sky will always exist, right? Sky will not exist. It does not, in this domain, these attributes, these dimensions always exist. So sky is representing a dimension of your particular data set. So say if I write sky equals sunny, so sunny is the value, right? Value of that particular attribute. In a way, sky is a variable, but now that variable is not the Boolean variable. Now sky equals sunny is a Boolean variable. This is the literal. So that is how you are forming these Boolean literals. So sky is sunny or not sunny? So when sky is sunny, it is true. When sky is not sunny, it is false. That means when sky is rainy, when sky is cloudy, it is false. Is it clear?
Yes, sir.
Yes, sir.
So similarly, you have other attributes like temp equals warm, humid equals normal, wind equals strong, water equals warm, forecast equals same. These are all variables. Now, in this function, when we say this, it is implicitly representing those variables. In this, so when we write it in the form of a function, it is not function. It is basically showing you the attribute values. These are the dimensions. So what we are writing in the conjunctive, conjunction form, that means sky equals sunny. I have already written it. Then and, so this is my and operation. I will be saying temp equal, let me write in a shorter way so that to save time. So T represents temp, say warm, temp equals warm, and like this. Humidity actually, that humid equals normal, and it goes like this. So you have 6 such thing. Then you are expressing something. Then you are expressing some fact, which means only when this is true, then this is true. Otherwise, the Boolean function, everywhere it will be false. Is it clear? So this is also a hypothesis. In a way, this is hypothesis. If I just take this one, it is an hypothesis.
Yes, sir.
Right? But does this hypothesis satisfy my whole training examples?
Not.
It's not only the first one, because
Yes,
I have
sir.
written only considering only the first one. So if I consider, for example, the second one, I can write also another hypothesis for the second one, but another, I say Boolean expression. Let me try. And then if I make, or say this one is for the second one, this one is the first one, and if I make an OR operation, then both of them will satisfy, isn't it?
Yes, sir.
Right? So in this way, you can express all the four tuples, all these four, I call this combination, sometimes we refer to that term tuple also. So even to a very technical term with respect to databases. So so when you consider each of these record, and for each one I am having the corresponding correct Boolean expression, I mean we convert them into Boolean and make the OR operations, then actually all four in this form they satisfy this training example, and that you in some way that is a representation, that could be a representation of a hypothesis which will at least satisfy this training example. But the problem is that it means that any other combination will always be false. So the prediction is very is very much biased with respect to your observation. So you are only allowing those you have observed. That is fine. It will be true for that if there is no error in your observations. But no, for all other observations, where unseen observations, so even when there are cases probably in the target functions, the target concept, they are true, but no, you will get false. So that is the problem of having such a trivial way of formation of hypothesis. And other thing is that you see that the I mean the expression itself, it takes so you are basically enumerating each and every tuple. So the size of your hypothesis is going to increase. Size of your hypothesis, if you consider the size of your formula here, that is going to increase with the increase in with the increasing set of training examples. As you go on observing more and more examples, you are simply adding them, like you are simply ordering all those expressions together. So this is also, in a way, this is an empirical way of expressing the thing, where instead of a table, you are just you can represent the whole thing in a table, which are only allowed, where you can evaluate. I mean, where there are truth values are there, you can say you can remove these things, right? When you are doing the OR operation, since this is false, you should not take this one, right? Only the positive examples will be now considered in this case. So, so there are certain other ways to represent this hypothesis. So this is one kind of Boolean, one form of writing Boolean functions, but we will use a bit more pragmatic form, but that would also impose certain constraints. Constraints in the sense that form will restrict me to not to use any many other Boolean expressions, right? Many other Boolean expressions in that form. So let me just explain what are those things are allowed. So in this case, just to summarize, as I was mentioning, that each constraint is a Boolean condition on attribute values, as I was explained. I just explained in that form. So so far I have given this example with a specific value. Say water equals warm, then either it is warm or not warm, and it will be true. But there is another form of representing Boolean literal, and which will give you a bit more power to express this kind of hypothesis in a concise form, but accommodating more general observations. I mean, more number of observations, more number of inputs into your positive set of positive examples with a concise representation of the formula. So one such case is, say, using a particular value of the attribute using a don't care symbol. That means whatever may be the value of that attribute set, it will be always true. This literal will be always true. So water could be either warm or it could be cool. Depends. I mean, I have to check what are the attribute values. So, but no, it will be always true. So that is the other literal, and also the other one, the opposite one, that in none of the cases, if whatever may be the condition of the water, this is always false. Now, when you are using conjunctive normal form, which means that conjunctions operations of each attribute conditions, which means that any attribute condition when it fails, which means the whole expression becomes false itself. So because of that restriction, there are a lot of redundancies also in our representation. So we'll come to that also. So if just I'm mentioning it here, just you please take note of this fact, and we'll discuss, we'll elaborate this later on. Right? So is it clear? This representation is clear. So in that case, I can write something like this, a valid expression. So, so as you can see, in a concise form, I can represent now in the form of a vector, which means every positions I will be, say in the every position will denote certain attribute. Will denote certain attributes. Say for example, first position is say for sky. So in that case, you are considering the value either sunny or cloudy or rainy. So if you go back to your example sets, just let me go back there itself. The first slide. Yeah. So you can see, so these are the conditions, right? So what are the valid hypotheses in this representation? With if I consider this combination, can you say, let me write something and you just tell me whether it is valid or not. I will be using a bit short form of attribute values. Just say sunny is represented by S, then humidity normal is represented by N. Say C is for temperature. Say W is for weak in the case of wind, and once again W is warm when it is water, and S is for say forecast, right? So this representation, what does it mean? It means conjunction of all such letters, that sky equals sunny, and humidity equals normal, and temperature equals cold, and wind equals weak, water equals cool, and forecast equals same. Now this is a hypothesis, isn't it? This is a hypothesis. Now if I just replace one field by this say question mark. Question mark symbol means here it is don't care state. It's a symbol. So which means it accepts every possible value for getting the expression true, when that literal becomes true for every possible value. Okay. So can you tell me that which are the combinations which are true? So this is also a hypothesis. So how many records will be true in this case? How many records will be true?
2.
Just a minute, I need to take a call. Just to
Yes, Manish.
I'm not saying anything. Swapnil. Can anyone repeat what is the last question that sir asked?
How many records will follow this hypothesis?
Will follow or will be true? I think
Will
the
be
sir asked.
will be true.
Okay. I think 2 की power 64 upon 2. Am I right?
Check from the
Let's wait.
Okay. So yeah, so the question I asked that no, how many records are there? How many combinations are there where it will be true?
Sir, 2 records.
Pardon?
Sir, 2 records only.
2 records, right? Say suppose this is question mark. How many? This is also don't care.
Then sir, 6 records.
Say this is 5. How many?
Then sir, 0 records.
Yeah. So wherever the 5 is there, it should be always 0 records, right? So that is a redundancy. That means this hypothesis, and if I have also another hypothesis phi here, that is also same kind of target concept. So that redundancy is also there, and also as I mentioned that these are the only form of functions that you are able to represent, which means I cannot represent a conjunct or sky is cloudy and humidity is high. That means that is one clause. Sky is rainy or sky is cloudy. Now that is not allowed. So I cannot write say S or R or C. In the attribute value, I cannot write that R or C. Then the rest of the things I cannot. I hope you have understood. No? I can have either all of them. Don't care. Either any of them is true means any of them will be accepted for the truth value, or only one of them would be accepted for the truth value, not any combination of them. So that is a constraint also imposed while expressing this conjunctive normal form. Is it clear?
Sir, I want to ask a question.
Yeah.
Sir, a given hypothesis will be true or not. It will be based on the given training example set.
Yeah. It will be. You can always test given hypothesis whether that hypothesis satisfies a training example or not. That can be observed. Yes, you can evaluate the hypothesis. You can get its value, and you can see that in the training example what is the value is given, whether they are matching or not.
Sir, in the
Are you saying
given,
that?
yes, sir.
Yeah.
Sir, you have write the first time the hypothesis. In this, wind is strong, but here you write the weak. Then there will be no record for this.
I don't understand that part. What you are saying? I write strong hypothesis. Can you explain me once again?
Okay,
So you
sir.
say wind is strong. You are saying wind is strong if I write
Yes.
it in the hypothesis. So what is the problem? Yes, I can write. I can express it. I can write here what is the position of the wind here. So this is the position of the wind, right?
Yes,
Instead
yes,
of
sir.
W, I can write here S. I can always write wind is strong. What is the question?
So, mm,
If wind is strong, this value would be true, right?
yes, sir.
Now, in a hypothesis, if there is something like wind is strong, then if wind is weak, then this combination will not be true.
Yes, sir. That's why I was saying when
So
wind
this is
is
the
weak.
idea.
Okay, sir.
Okay, so let me just go again proceed. So these are the form of target concepts that we are considering. I'll just start. Right. So as I was mentioning that these are the only forms for any literals to be expressed. And as also we have seen with illustration that now we can represent a hypothesis in the form of a vector. So instead of writing all those expressions with equality operator, etc., I will simply list those attribute values, including also this don't care value and also phi value, null value. So including them, so I can write any conjunctive normal form expression using them. Yes. What is the question? Please mute yourselves. So these are the examples like sky, attempt you made in
ఇది
what
కదా
I think somebody's microphone is
ఇది
still
కాదమ్మా
off.
చారంలో ఉంటది కదమ్మా అది
చాలాలో ఉండిరా
వస్తుందా
మరి పెన్ డ్రైవ్ కాదంటారా
అది కాదమ్మా చారంలో
I think
ఉండేది
somebody is talking. Please mute yourself. Right. So this is you can see that this hypothesis that sunny question mark strong question, I'm reading them as question mark. It is basically don't care, and then send, right? So and given any particular combination, you have to test whether this is whether this is satisfying, whether it is true or false, whether this hypothesis is true or false, based on this representation. You can always find out. You can always, if I go back to a table and you can get some values and you can see that whether it is true or false. So it is represented as a vector, which is an element of the 6-dimensional space. Okay, so this is just example. That's what I will. So can you tell me what should be the value? Say the first one. First one, what should be the value of age?
Sir, sunny, warm, normal, strong, warm, and same.
That would be
Yeah.
1.
Yeah, it is satisfying. And the second one?
That will be
Sunny, warm, high, strong, warm, same.
0, sir.
0, sir.
It
0.
is?
0.
forecasting value is in
It is not satisfying this part. Now this change.
Humidity.
It is not
Yeah.
satisfied. This one. And which one you are saying is not satisfying? Others are satisfied.
Sir, third one, sir.
No, but third one is admitting any value, na? So it is satisfied.
Okay, sir. Okay, sir.
That is
Yes.
satisfied.
Yes.
So only this value is not satisfied. And in the conjunctive expression, that means all are ANDed, so you will get 0. So that is the idea.
Got it, sir.
So this is what we have to understand, that this is with this representation, whatever possible hypothesis that you can form, that will give you the space of hypothesis. As I mentioned, many of the other forms of Boolean expressions are not admissible. Only the admissible forms will form this space of hypothesis. Right? So now I will ask this question, that all these questions, we have already asked this question, what is the size of input space and size of H? No, we have not asked really in that sense. So I will go back to that once again to the first slide, and you should tell me these two numbers. What is the size of input space X, and what is the size of hypothesis space, right? So please tell me those numbers. Let me again go back to that first slide, just to give you, yeah. So now you have the whole problem statement, that these are the possible set of attributes. These are the set of attributes, and also the possible set of values for each attributes. Those are given to you, and they will give you the corresponding input data set. And based on the input data, you are evaluating a function, Boolean function, in the form that I mentioned, that each attribute will have a place in the conjunctive expression by forming a literal, which means that attributes equals either some specific value or don't care value or null value. And then you are having AND operations with that Boolean conditions. So each attribute will give you a Boolean condition. Okay, and whatever value you evaluate using that Boolean algebra, you will get that value will be your functional value, which is in the form of true or false, or 0 or 1, whatever you say here in this case. So this is the idea. So now you tell me that how many possible combinations are there? I mean, how many possible input points are there?
Sir, 96, I think.
96, huh? So you are just simply multiplying, isn't it?
Yes.
3 into 2 into 2 into 2 into 2 into 2. Okay.
Yes, sir.
So that would give you 96. Then the next question. So how many possible hypotheses is there?
2 की power 96.
2 to the power 96. That you are saying 2 to the power 96. Yes. That is also true.
973.
But no, there are some other expressions are also possible. No?
The 973.
Yeah. So you are telling something. I mean, I hope you have read the book already. You are giving me the answer to the quiz. But no, can you explain me?
Sir, in the sky condition, there can be a don't care. In each condition, there can be a don't care value. So it will be 4 into 3 into 3 into 3 into 3 into 3, and there will be that 5 in that it will not accept for
So it
any
is a
case.
question of no hypothesis. You have already the combinations. No? So how many combinations of hypotheses is possible? Like the number of combinations have given you the input set, but what is added for each one? What is added for each one? For each one, we are adding 2 more symbols, 2 more attribute values. One is don't care, another is null. So for sky condition, how many literals are possible in that case in the hypothesis space?
5.
5. For humidity, it is 4. Temperature, it is 4. Wind, it is 4. And water, it is 4. And forecast, it is 4. Is it clear? Is there any doubt? So if I multiply this number, that means I have 5 for sky and humidity 4, temperature 4, wind 4, water 4,
5120.
and forecast 4. I hope you have understood, no? I mean, why it is? Because I am adding also. Say I will show the example just for the sky condition and rest are the same. I'm adding this 2 more attribute value. So 2 more literals that can be added in the hypothesis, in the formation of hypothesis. So these are the possible, no, this is the number of possible hypotheses. So if I multiply them, what should be the number?
5120.
5120.
Something like 5,000 something, huh?
120.
120.
5120. That's what you told, no? Okay.
Yes, sir.
So this is a possible hypothesis. Right. Now the question is that, as I mentioned, there are many redundant hypotheses because they represent the same concept. And what is that? That if any of these value is 5, if any of the attributes value is 5, literal has 5, which means no, always the function would be null, the functional value would be null. So they are non-distinct. So how many distinct hypotheses? If I ask you questions, how many distinct hypotheses is possible? In that case, what you should do that you consider all the literals without 5.
Yes,
All
sir.
the
Right.
literals without 5, which means it is 4 cross 3 cross 3 cross 3 cross 3 cross 3. Some number will come. And then you add that particular functional form, that value will be always null. That means which represents any functional form where there is a literal 5, literal with 5. Okay? Is it clear? And that value is coming 973. I hope it is clear.
Yes, sir.
Yes, sir.
Okay. So let us proceed. Yeah, so we are here. So finite number of combinations, as we see. So size of input space will be cardinality of these sets, sky, temp, humid, and this is the value. Size of hypothesis. So I have already mentioned that no, each attribute can have so many literals, and if you multiply them, you will get this value. But since there is a redundancy, finally you will get this distinct hypothesis. Number of distinct hypotheses would be 973. So task, I hope you have understood that if I give you a set of training examples with that kind of representation, with the attribute values, then you have to predict the corresponding target function, right? So this is already I mentioned. I mean, we have already discussed, so there is no point repeating them further. Well, experiences are those training examples. So training examples can be also represented a bit more formally in this form. Like, you can see that a bit formal representation. Just note this: X is a set of examples, set of instances or training examples, whatever you say. No, not say. Sorry, set of instances. That's the input space. Any element of the input space. Or the input space itself. And the training example set is represented in this way. And each training example looks like this. That means you have the corresponding input value, corresponding point in the input space, and the corresponding functional value, which is given in the form of yes or no in the case of table. I hope this representation, this mathematical representation is clear to you. And there has to be a performance measure, as we have discussed, that when you are learning something, there has to be a performance measure. In this case, we will be very conservative. We will assume there is no error in the training data set, which means I have to satisfy at least all the training examples. That is my performance. So if it is not satisfied, then no, I cannot accept that hypothesis. If any of the example is not satisfied in the hypothesis, satisfied doesn't mean true. No? Satisfied means even negative examples should be also satisfying the functional value. Okay, so that is what. So the hypothesis H in the hypothesis space such that at least it should have the corresponding functional values of the target function, partially which are given to you as in training examples for all of them. And you are assuming, you are putting these hard constraints with the assumption that you do not have any error in your observation. Then you are fine with it. You at least try to fit whatever is given to you. But as I have already mentioned, that even for doing that also there could be various alternative hypotheses. So there is no unique solution. There is no unique solution. So what is the thing again? No, which solution then I would consider better? So I can get any solution. So that the concept of minimality is coming there. So we would like to keep it minimal also. But as far as the representation, even what we have, we are in the representation itself, it has been concise. But again, the minimality considerations, we will see it has further meaning in this case. That means there could be hypotheses which are more general to any hypothesis. Both are satisfying. Both are satisfying all the training examples. One of them could be more general, another could be more specific. So we may choose more specific one. Anyway, it depends upon you. Sometimes even when we say more general, there are certain connotations with that. We will discuss that part also. But before proceeding further, and in fact today the time is almost over, so let me finish this slide and then I will take the attendance. So here our assumption of inductive learning is considered. So what is inductive learning? It is basically learning from examples in a very crude way of saying that. So you assume that whatever property you observe with the examples, now that property could be extended on the unseen data also. So that is the property of induction. So that is what it is saying. So let me not just proceed further. So let me stop here for the discussion, and also let me take the attendance first.